Good morning. We're going to try to discuss radiative heating in numerical models via a little Camtasia video. And as I did last week, I'll try to make this video in one fell swoop, and I'll do it again if it's really cruddy. So we're talking about radiative heating. Courtney has already expressed distress at my handwriting on my tablet device, but that's just too bad. When it comes to the topic of radiation, I am completely overwhelmed by the complexity of it. Every textbook contains thousands of pages of integral equations, which I don't like anywhere near as much as differential equations. And it's clear that this is something we could spend the whole semester talking about. On the other hand, our textbook by Warner has almost nothing. So what I'm going to try to do is explain radiative heating in models in about 11 steps, building up to what's actually in models. So we're going to start with, what are we going to start with? Let's go ahead and open up a fresh sheet here. And let's start out with shortwave radiation, which is the ultimate driver of all the motions that we really care about. So let's think about shortwave radiation. That doesn't look good, does it? Okay, let's try again. All right, shortwave radiation. So we always pictorially display this as a bunch of squiggle heading down from the top of the atmosphere to the ground, where heating is caused, and that's what heats our atmosphere. It's kind of strange. Our atmosphere is heated from below by the sun, but nevertheless, that's what happens. But in reality, some more complex things happen, so let's try to do that. So this is our shortwave radiation coming in, but on the way down, let's choose a different color. On the way down, the shortwave radiation stream is going to intercept a bunch of things: atoms, molecules, bits of grit, clouds, you name it, and all of those are going to mess with the downward flow of energy, and all of which have to be taken care of. So let's thin out this a little bit. So we're going to need to deal with absorption, which I can't get on the page, so we'll leave it just like that. We're going to have to deal with scattering, and we're going to have to deal with reflection. Whoops, FLN. Oh, I don't know what's happened. All right. We're going to have to figure out all of that so that we can ultimately decide exactly how much radiant energy is getting to the surface. So let's start by looking at the issue of the absorption of radiation coming in. And so when we have an atom, there's something in the middle of it. And then you have, this is not good, you have electrons orbiting. There's one electron. I do not know why the line type is dash. Let's try this. And then along comes some radiation. That's not going to do it, is it? Along comes some radiation. Okay, let's pause the recording. All right, let's consider a single atom which has an electron in orbit around it. It doesn't have to be one electron, but it could be multiple electrons. And in comes some solar radiation, which we write as h nu. H is Planck's constant. Nu is the frequency of the radiation, so this is an amount of energy that's coming in. And what can happen is that the electron is excited, and jumps to a higher orbit, higher energy level. And these are discrete energy levels. So this is all stuff from quantum mechanics, but we'll just take it as true. And so this is what the process of absorption looks like with an individual atom. Amount of energy h nu is absorbed, and it does so by this electron jumping to a higher energy level. And then, of course, at some later time, the electron can jump back actually to a lower energy level, and that's when you have the emission of energy by the atomic species. Okay, so we're in 11 steps here. This is step number 2. I forgot to mention step number 1 earlier. If this is something you're not very comfortable about, then I have here a Khan Academy mini video keyed up for you about absorption and emission, and you can see the URL up here. It's not fantastic, but it's better than nothing. So now, the third step in the process is what happens to, so let's just put a 3 here somewhere. We've seen what happens when solar energy comes in and is absorbed by atoms, but most of the atmosphere, at least the part that we care about, is not atoms, it's molecules. And the ones we care about the most are water vapor, carbon dioxide, things like methane, and so forth. So we need to understand now what happens when these molecules absorb radiation. So for molecules, I've seen some videos like this before whenever I teach MET 60, so I thought it'd be a good idea to show you again. So here's a link to somewhere in England.uk, and this is about the absorption of radiation by water in the atmosphere. And so you can see what the URL is up there. And the thing that I wanted to focus on is this. So water is a molecule, H2O, 2 hydrogens, 1 oxygen. So the red thing here is the oxygen atom, and the 2 gray things are the hydrogen atoms forming the molecule. And when radiation energy comes in from the sun and is absorbed by water vapor, likewise long-wave radiation, then the molecule can move in all sorts of interesting ways. So you might also have that electron jumping to higher orbits stuff, but the molecules now move. They can move lengthways. I think that happens with CO2. They can do these other things like vibrating in multiple different ways. And each of these allowed behaviors ends up appearing in the form of a spike in an absorption spectrum somewhere. So if we go back to my drawing pad here, and just open up a new drawing pad, then what you're going to get is an absorption spectrum looking something like this with, let's see if I can make the lines a bit fatter, with lines representing the absorption by a given species at a different wave number. And I mean, this is just completely made up, doesn't represent anything in the real world, but you get these absorption spikes. In other words, instead of all of the light being transmitted through the atmosphere, and this holds true for long wave and short wave, some of it is being absorbed at discrete wavelengths due to, this needs to be a new here. Let's fatten up new there. Okay, so this is all due to the individual behaviors of individual molecules. The next problem is that because of the interactions between molecules with neighboring molecules, you don't see pure spikes like this, but instead you'll see something more like this. You'll have a thing going on called pressure broadening, and then you've got these absorption bands overlapping with one another. Excuse me, I'll just turn my phone down. All right, and why am I telling you this? I'm telling you this because this is the level of complexity that's really happening in the atmosphere, and therefore this is the level of complexity that has to be modeled in a GCM, in theory anyway. So again, although I started out by talking about shortwave radiation, most of this shown in this diagram obviously is for long-wave radiation. But the same holds true. This is an example of the transmission of radiation through the atmosphere as a function of wavelength in microns. So visible light is down around here at 0.5 and everything else is in infrared. There's a lot of transmission in the visible part of the spectrum, and in this part of the spectrum between about 8 and 11 microns, which is called the atmospheric window, but then on the other hand, there's a huge amount of absorption that's shown in very complex ways by these wiggles here. And this is the impact of individual molecules and species of molecules in the atmosphere, absorbing radiation, including effects like those rotational and vibrational effects that are going on inside the molecule. If we click on this one down here, which is a close-up, I think you can click on this too. Yeah, there you go. So this is from just beyond the visible part of the spectrum down to 5 microns, and you can see it's hugely, hugely complex. So if I go back to something that I might now have destroyed. Yep. All right, well, I'll just make a new one. If I go back, I had to destroy the first one because I had a little bit of an accident, as you can probably imagine. If we go back just to the idea of shortwave radiation coming down through the atmosphere like this, and trying to model the absorption of that radiation in the column between the top of the atmosphere, where officially there is no atmosphere, and the ground, GD, it's an immensely complicated process. More so for long-wave radiation because of all the selective absorbers in the atmosphere, but also for shortwave radiation. There's atomic species in the very high atmosphere, and they do their share of absorbing. And we need to be able to replicate this in our models for reasons that'll show up shortly. And as you can no doubt imagine, when you put a cloud in here, and we'll have a nice red cloud, then all kinds of extra things happen. The cloud has an albedo, it causes some reflection, but there's also now liquid and vapor water in here, and that has to be factored in too. And of course that means you have to get the profiles of temperature and vapor correct in your column, so you can get the right amount of clouds in the right place at the right altitude, so that you can get the correct radiation incoming down here at the ground. Now, I've lost track of my steps. I guess I could tidy this up later on, but let us, I did look at this to try to make it default, but I couldn't make it default. This is, believe it or not, step 7. No, it's even worse than that. It's step 9. And step 9 is the long wave radiation. In a simple situation, you would just have long wave radiation leaking out to space, but of course we don't have that going at all. And in fact, if we did, it would be far more boring. So in reality, what we think about is individual layers in the atmosphere that have long wave radiation welling in up from below, being absorbed inside those layers, and then being re-radiated both upward and downward. The downward radiation might make it to the ground, so that has to get factored in, or it might be absorbed and then re-emitted from a lower layer. Again, this is going to be very complex because we're going to divide the atmosphere into layers and do this sort of layer by layer calculation of how much radiant energy goes up, how much of it is absorbed locally to cause heating, and so on and so forth. And then, of course, when we put clouds in there as well, and let's have stratocumulus clouds this time, that'll make things even more complicated. So when you look at radiation studies, you'll see shortwave clear sky, shortwave cloudy sky, long wave clear sky, and long wave cloudy sky calculations being discussed. So step 10 then is to look at the net radiative heating as a function of height. Actually, there are two things that we want to get out of our radiation code. First of all, is as a function of elevation at each grid point, I guess, what is the net heating or cooling profile that we have because of solar energy. So I'm fairly confident in saying that solar is going to be heating, but we'd like to know what it looks like exactly. And then infrared is going to be cooling throughout the column most of the time. And then there's going to be a net represented in purple. And if that was 0, then we'd have no heating going on in the atmosphere, and that clearly isn't the case. So I dug out a publication, and it's in AGU. It's an AGU publication, and you can see the URL up at the top here. Well, okay, let me go up to the top and show you what the title of the paper is. Analysis of tropical radiative heating profiles, a comparison of models and observations. And there's nothing particularly about tropical that I chose here. It just happened to be the first thing that I found. So, and one of the nice things about this is that they show heating profiles from observations and models for both clear skies and cloudy skies. So now I'm trying to find those quantities. I know I want figure 9. So figure 9, these are heating profiles from 3 things. Let's read down at the bottom. From observations in the solid line, so you can see that a little bit in the diagram here. And then from one simulation with a dashed line and a second simulation with a dotted line. So let's look at this. And looking again, the left-hand column is the long wave radiation. The middle column is the shortwave contribution. And then the right-hand side is the net. And this is at some tropical location. So what do we see? Let's look at the first diagram here. So this is elevation from sea level to 20 kilometers, and that's the same in each panel. And along the bottom is heating rate. And for the long wave portion, this is the 0 axis here. So everything to the left of there represents cooling. And as you can see, all the way through the troposphere, long wave radiation is cooling the atmosphere, and that's what the solid line shows. And then the other two lines are calculations by models to try to reproduce that. To me, it looks like they're pretty good, although they might be off by a tenth of a degree per day. The heating rate is expressed in degree per day. Second panel is the shortwave heating. So here's the zero. The shortwave isn't going to do any cooling, so it heats throughout the column, and it heats at a rate of just under 1 degree per day, peaking at about 7 kilometers and then a little bit less above and below. Pretty small heating rates up in the stratosphere. And then the thing that we care about is the net. So in the net column, at this particular location, it's net cooling. I don't remember my global circulation modeling observations well enough to remember if that's representative or not. But the point is that this is based on observations at this particular location under clear sky conditions. And the important thing is that whatever models they're looking at have gotten that fairly well. So in terms of general circulation models, we have to reproduce the shortwave heating, the longwave cooling. We need to get the correct net profile. And it would be nice if we could compare those to observations and have some kind of validity. So finally then, how are we going to cram all of this information into a GCM? How could we replicate all of this information accurately? And so the answer to that question is by something called a line-by-line radiative transfer model. And if I write this out longhand, it's going to drive Courtney crazy, so I'll just say it again. Line by line radiative transfer model. And line by line means that, you remember that pretend diagram I showed with absorption lines? Drat, I hate it when I can't find anything. Well, all right, so let me just do this again. Line by line means that you move along the frequency axis, or you could invert this to have this be the wavelength axis. And at each line, you do a full calculation of how a particular species interacts with radiation in terms of absorption and so on and so forth, in very thin intervals of frequency or wavelength in microns. So let me find a line-by-line model to show you. So this seems to be the main one, the Atmospheric and Environmental Research Radiative Transfer Working Group website. So these people have built a line-by-line radiative transfer model, LBL-RTM, that should be the closest thing to perfection that you could find. And what they are doing is constantly trying to update the line-by-line code. So looking over here at the exam on the left-hand side, description, that is not a description, I'm sorry, but okay. Line-by-line RTM attributes provide spectral radiance calculations with accuracy consistent with measurements against which they are validated, and computational times that facilitate the application. So line-by-line code is very computationally expensive, much too expensive to use in an actual GCM, but you'll see where I'm going with this in a minute. Sorry, I had to pause, airplane going overhead. The line-by-line code imports into it something called HITRAN, uses HITRAN, and I'll let you look that up. on Wikipedia, although I suppose I might, yeah, I've got a little icon here. HYTRAN is a database of the parameters you need to calculate the transmission of radiation through an atmosphere filled with whatever quantity you want it to be filled with. So if you wanted to look at transmission and absorption in a methane atmosphere, HYTRAN would have that information for you. It's been under development since I think the 1960s. Let's see, aerosol properties. Let me see if it's got, no, that's no use. Here are the molecules that you can have in HYTRAN: water, carbon dioxide, ozone, carbon monoxide, methane, ammonia, nitrogen, ethane, and all the way on down. And for all of these compounds and all the different isotopes, it'll give you the parameters that you need to calculate your own spectrum. So the line-by-line RTM model uses some HYTRAN information, and then, I mean, here you go. HYTRAN line database parameters are used, blah, blah, blah. Let's see. Code and examples. No, let me go back to this. So the line-by-line code is computationally demanding, and so models use, and this is where we come to the end of the story, you'll be happy to know. So let me have a new one of these, and a whole new pencil, and a whole new color. So this is point number 12. I don't remember how many steps I said that there would be, but final acronym for the day, RRTM. Okay, and this stands for the Rapid Radiative Transfer Model. Now, how I got to this is by reading about the ECMWF model and looking to see what radiation code they use. And they use a version of the RRTM code. So then I went looking for what is the RRTM code, which took me to the line-by-line code and back to the beginning with the absorption of radiation by an atom. So models use something like the RRTM code, which is a rapid version of the line-by-line code, which exists because of the reasons that I've been through in this lecture. So if we go back to the home page for these people, at the AER, over on the left-hand side, you'll see the products that they offer. The line-by-line radiative transfer model. And then down here, we've got the RRTM rapid radiative transfer models. And I think the ECMWF explicitly uses the RRTM-G model. These are very recently updated. RRTM retains the highest accuracy relative to line-by-line results for single column calculations. RRTM-G improved efficiency with minimal loss of accuracy for GCM applications. Okay, so RRTM, this is what it does for the long wave portion of the spectrum. RRTM, this is what it does for the short wave portion of the spectrum. RRTM-G, long wave and short wave, these are the bits of code that go into the general circulation model. And let me just go back and see if I can find that thing. I don't know if I'm going to be able to. Yeah, here it is. This is the radiation code in the ECMWF model. And what do they say? Their radiation code is based on the Rapid Radiation Transfer Model, RRTM, developed to AER with a reference to. I want to go back to something over here that I forgot to completely finish saying. I wonder if it was this one. All right, let me start a new one because this is an important thing to finish up and consider. So let's go with orange. So we have the ground and we have the top of the atmosphere. Whoa, that didn't go well. Oh, you know what? I'm doing this with my Mac and not my silly pencil. All right, so there's the top of the atmosphere, which probably does have a tidal bulge in it in the sunlit portion of the planet. So we've got short wave coming down and long wave going out. And what we need to know for our GCM is two things. First of all, for each level of the atmosphere, in each layer, we need to know the heating rate. And that'll go into our equation for the rate of change of temperature with time. Inside, let's say, this one little box here, it's going to be due to advection and so on and so on and so forth, and heating rate due to radiation, which in some of the places we've written it as Q sub R. All right, so that's one thing we need to know, and that's why we need a radiation package. The other thing we need to know is the net heating down here at the ground. The shortwave radiation is going to do some penetrative heating into the soil, so we're going to have a soil model. Sorry, my hand slipped. We're going to have a soil model here to heat up some of the soil, and then some of that heat from the surface is going to leak into the atmosphere in the form of long-wave radiation, sensible heat flux, and latent heat flux. And all of that is the topic of the next chapter. But we need to know what the driver for this is, and that's the radiative heating at the surface. So we need to know about radiation to tell us about the heating rate in the column and also what goes on at the surface.